Hello. In this video, our goal is to present a few more examples of strong induction. We also want to talk a little bit about base cases and how you know how many base cases you need to make a strong induction proof work. All right, let's jump right into our first example. Let's suppose that we're trying to prove the theorem for all integers n greater than or equal to 0. We have 10 dividing the integer n to the fifth minus n. Now, to make sense of this statement, you might consider a few values of n. If we plug in 0, this says that 10 divides 0, 0 minus 0. If we use n equals 1, this says that 10 divides 1 minus 1. For n equals 2, this is the statement 10 divides 32 minus 2. And so we're going to prove this is true for all n greater than or equal to 0. And the way we'll do it is by induction. And as you'll see in a moment, strong induction is the one that's going to make this one work. At least the most clearly. All right, so if we start off with strong induction, we would start with our base case. Since we are looking at all integers n greater than or equal to 0, 0 is certainly the one we should look at. And since 10 does go into 0, the base case clearly holds. Now, we're going to leave as a question whether or not other base cases are necessary. And we'll come back to that question a little bit later when it's apparent what the answer should be. Now, with our strong induction hypothesis, we would suppose that all of these statements were true for all values of n from the beginning up through the kth statement. So another way to say that with notation is to say that we're going to suppose that 10 divides I to the fifth minus I whenever I is anything between 0 and k. So we're supposing that all of these statements are true for every value from the beginning, 0, all the way up through the kth statement. Now we need to show that the claim holds for the k plus 1th statement. Now in order to claim or to show that 10 goes into k plus 1 to the fifth minus k plus 1, we need to show that k plus 1 to the fifth minus k plus 1 is 10 times an integer. And so that's our goal. We want to figure out what goes in there. And what we'll do is just try and manipulate this expression. K plus 1 to the fifth minus k plus 1, what is that equal to? Well, if we expand that all out, you'll see that the k plus 1 is equal to k minus 1 plus 2 raised to the fifth. And if I write k minus 1 plus 2 in place of each of these k plus 1s, and then expand, keeping the k minus 1s together, you'll see that the first part expands in this long expression, and the second part, the k minus 1 plus 2, I can rewrite that as minus k minus 1 minus 2. Now, why did we do this? Why did we keep the k minus 1s together instead of the k's? Why didn't I just expand this out as k to the fifth plus a 5k to the fourth and so on? Why did I keep k minus 1? Well, I did that so that I could have this 2. Now, as you're distributing this out, you'll see that with a combination of the 5s that come from the exponent and the 2s that come from the 2 in our factor, the coefficients just magically work out so that each coefficient is divisible by 10. Now, when I take a look at this now, I'm going to take this k minus 1 to the fifth and the k minus 1 and group them together, and then everything else will have a 10 in the coefficient that I can factor out. Now, this is great, because remember that we said that the statement 10 divides n to the fifth minus n was true for every value of n up through k. And so we recognize here k minus 1 to the fifth minus k minus 1 as n to the fifth minus n with k minus 1 plugged in. Now, since k minus 1 is in that range, we know that k minus 1 to the fifth minus k minus 1 is divisible by 10. It's going to equal 10 times an integer c. So I can just take this expression and replace it by 10c, factor a 10 out of everything, and then continue on. I'll just say that since this expression I factored 10 out of is an integer, we conclude that actually 10 does go into k plus 1 to the fifth minus k plus 1, and our proof by induction is complete. All right, now how do we use the strong induction hypothesis? Well, we used the fact that k minus 1 was one of these values that we claimed the statement held for. Why did we need k minus 1? Why did we need strong induction rather than ordinary induction? Well, again, it's because we chose the k minus 1 so that when we expanded this out, keeping the k minus 1 together, the coefficients worked out very nicely. That will not happen if you just break up k plus 1 to the 5th if you expand that out as we normally would. All right. Now, we haven't answered this question. Are there other base cases necessary? And let's take a look at how we'll decide. Now, one thing you'll need to pay attention to whenever you're working with a strong induction proof is that the value of n you're using the induction hypothesis with does in fact fall into the range of values you supposed the statement to hold true for. Now remember, we supposed that 10 divided I to the 5th minus I whenever I was anything between 0 and k. Now we used that fact by replacing k minus 1 to the 5th minus k minus 1 by 10 times an integer. Now we can do that as long as k minus 1 really is inside that interval. Now k minus 1 will always be less than or equal to k. There's no question about that. But as you take a look at the other side of the inequality, you'll notice that actually this part of the inequality doesn't work if k were equal to 0. If k minus 1 is greater than or equal to 0, that requires that actually k be greater than or equal to 1. All right, so we can change that. We'll just suppose that k is greater than or equal to 1. But now this is going to tell us whether we need more base cases or not. Remember, with strong induction, what you're going to do is suppose that the statement you're proving holds for all values from 0 up through k. In other words, k is the last statement you know or suppose to be true, and then you're going to go ahead and prove it's true for k plus 1. Well, if we need k to be greater than or equal to 1, and k is the last statement we know for a fact that the claim is true for, then we need to verify our statement not only for k equals 0, but for k equals 1. So let's take a look at this. If we were to make sure that the statement was true when n equaled 1, we would just take our original base case 0, that needs to stay there, but we'll add another base case so that when we say, assume that k is greater than or equal to 1, and now let's take a look at k plus 1, that k being greater than or equal to 1 is something we can definitely claim because we did go ahead and verify all the base cases up through the case 1. All right, now that's going to be how you'll decide whether you need more base cases in any strong induction example. You want to take a look at the values of the previous values of n that you used and make sure that those values, which in this case were k minus 1, lie in the interval that you supposed the statement to be true for. Let's make this a little bit clearer with another example. Let's suppose that Gn is a recursively defined sequence. We're going to suppose that G1 is 1, G2 is 2, G3 is 6. And we're going to say that for every value of n greater than 4, greater than or equal to 4, you can compute Gn by just taking n cubed minus 3n squared plus 2n and timesing it on to the term 3 steps before. So in other words, to find out what G4 was, I would plug in 4 in for n. I'd see that I just take G1 and times it by 4 cubed minus 3 times 4 squared plus 2 times 4. Now, if you write these terms out, you'll see that actually they do look like a factorial. G1 looks like 1 factorial, G5 looks like 5 factorial, and so on. And so we want to prove this statement. Now, to prove that for every n in the natural numbers, Gn actually equals n factorial, we're going to use induction. We're going to use strong induction for a reason you'll see in a second. Now, with any induction proof, we're going to start with the first n we're claiming the statement for and verify that the statement is in fact true for that n. Since the first natural number is 1, we need to verify that G1 equals 1 factorial. Now, G1 we were told is just equal to 1, and 1 factorial equals 1, so the claim is true in that case. Now again, we're not going to know until later whether we need more base cases, so let's just go on with the induction step. Let's suppose, as we would with strong induction, that we have a value of k greater than or equal to 1, and let's suppose that our claim, Sn, is actually true for all values between 1 and k. Right, now we need to show that the statement is true with the k plus 1. Gk plus 1 is equal to k factorial. So to do that, I'm going to just try and simplify this, fill in the details here. Now what do I know about gk plus 1? Not much, except I have this formula for computing values of g. So let me use that formula. I'll say that gk plus 1 is equal to k plus 1 cubed minus 3 times k plus 1 squared plus 2 times k plus 1 times gk minus 2. You'll notice that k minus 2 is what we get if we put k plus 1 in this n minus 3. Now, saying that, I can go ahead and now that gk minus 2 is the term I'm dealing with, and I supposed that gn was equal to n squared for all values up through the kth, and k minus 2 is less than or equal to k, I should be able to just put k minus 2 factorial in place of that gk minus 2. Now if I do that, I can go ahead and start multiplying this all out. When I simplify what's inside the brackets there, it just becomes k cubed minus k. I'm going to times that onto k minus 2 factorial. And then I'm going to take k cubed minus k, and I'm going to factor that. If I take a k out, I'll have a k squared minus 1, which I can then factor as a difference of squares. So k cubed minus k factors as k plus 1 times k minus 1. Now k minus 2 factorial, you'll remember, is the product of all the numbers from k minus 2 down to 1. So as I look here at this row, I've got the product of all the numbers from k plus 1 down to 1. And so that last last row we've mentioned is actually equal to k plus 1 factorial, which is exactly what we were trying to show gk plus 1 is equal to. So we should be done with our induction step. And we're done with our proof as long as the base cases are okay. Now again, how do you know which base cases you need to do? Well, you need to take a look at where you use the induction step. And you want to make sure that the value you used it, the value of Sn, the value of n you used, lies in the range you assume to be true. So now we used the fact that gk minus 2 was going to equal k minus 2 factorial. So k minus 2 is the value of n we needed to use the induction hypothesis for. Now that just means that k minus 2 needs to be between 1 and k. Now k minus 2 is definitely less than or equal to k, but we need k minus 2 to be greater than or equal to 1 in order to be able to use that induction hypothesis and substitute k minus 2 factorial in for gk minus 2. Now that's going to be true not just if k is greater than or equal to 1. Actually, if we solve for k in this left-hand inequality, we're going to see that k needs to be greater than or equal to 3 in order for that step to be valid. Now what? Well, remember, we were supposing that the statement is true for all n's between 1 and k, and then we're going to prove that it's then true for k plus 1. Now, if k is the last statement you know for sure the claim is true for, and here we're saying k is greater than or equal to 3, then we need to verify this statement for all the base cases 1, 2, and 3. So we will go ahead and throw some extra base cases in. And once we do that, once we verify that g2 is 2 factorial and g3 is 3 factorial, we know that the claim is definitely true for all values up through the third value. And so I can therefore confidently say that I can let k be greater than or equal to 3 and prove the statement for k plus 1, and I'll know that I haven't missed any values of n in showing that gn is equal to n factorial. All right, now this completes the proof. To complete our video, we'll take a look at one final example, and we're going to start with the question. We're going to ask which positive numbers can be written as a sum of 3's and or 5's. Now when I say a sum, I just mean an expression involving 3's, 5's, and or addition. So even though I don't see an addition sign here, there is a way of writing 3 as a 3's and or 5's. So I'll say that you can definitely say 3 can be written as a sum of 3's and or 5's. And 5 definitely can as well. Now as I look at the other ones, 1 and 2, it doesn't look like I can. 4, there's no way to combine 3's and 5's with addition to make 4. But 6 I can. 6 is 3 plus 3. 7, I don't really see a way of adding 3's and 5's to make that. But 8, definitely. That's 5 plus 3. And 9 is 3 plus 3 plus 3. And 10 is 5 plus 5. Now as I go along, I'll see that 11 is 5 plus 3 plus 3, and 12 is a bunch of 3's added together, and 13, and you might start to suspect from these last two columns that actually every number from 8 on can be written as a sum of 3's and or 5's. And so that's what we're going to try and prove. We're going to show that every integer from 8 on can be written as a sum of 3's and 5's. Now maybe as you take a look at these examples, you can start to see what the idea is going to be. You'll notice that as I take a look at the additions in any row, there's something in common there. You'll notice that on this middle row, we just had a bunch of 3's. We had one more 3 each time. Now in the top row, we had that same pattern. You started off with something, in this case 5, but then these other columns are just adding 3's onto that. And that seems to make sense. If you were able to do something using 3's and 5's, then the number 3 later should just have an extra 3 attached to what you had in the previous column. So for 11, because it's 3 more than 8, I can just take what I did for 8 and tack on an extra 3. Well, let's see how you would write that up in a proof. We're going to use strong induction, and the way we'll start our strong induction is the way we do any induction proof. We're going to verify the statement with our base case. Our base case is the first value that n can take on according to the statement of your theorem, which in this case is 8. We need to verify that 8 can be written as a sum of 3's and 5's, and that's done right here. 8 is 5 plus 3. Now again, we'll decide later if we need more base cases, so we'll just continue on with the induction by making the induction hypothesis. We're going to suppose that k is some number such that each of the integers from 8 up through k can be written as a sum of 3's and 5's. Our goal is then to show that k plus 1 can also be written as a sum of 3's and 5's. Now, k plus 1, remember, is just 3 more than k minus 2. Now, our trick that we talked about on the last slide, if we know we can write k minus 2 using 3's and 5's, then I could just tack a 3 onto that, and that would give me a way of writing k plus 1 as 3's and 5's. So to say that again, if k minus 2 lies in this range, by the induction hypothesis, we know that k minus 2 can be written as a sum of 3's and 5's, and by adding an extra 3 to that sum, whatever it is, we will get an expression of k plus 1 as a sum of 3's and 5's. Okay, now here's where we be careful again. In order to make this work, this k minus 2 needed to be a sum of 3's and 5's. Now I suppose that everything from 8 to k was a sum of 3's and 5's, so I just need to make sure that k minus 2 lies in this range. In other words, that k minus 2 is greater than or equal to 8 and less than or equal to k. Now the less than or equal to k part will not be a problem at all, but the greater than or equal to 8 is something I need to pay attention to. That's not going to be guaranteed by just taking any old k that's greater than or equal to 8. In order for this part of the inequality to be true, k will have to be greater than or equal to 10. Now remember, k is the last value you know the claim is true for, or that you're going to assume. And so in order to say that k is at least 10, I need to verify my base cases up through 10. So I need to start at 8, but I need to keep going until I verify the statement true for n equals 10. Well, that means I'll tack on the claim for 9 and the claim for 10, and then the rest of the proof will continue as it's outlined there. Now, the base cases here, you'll probably see they kind of make sense. As we go back to the examples we had before, in order to show that everything worked from then on, we needed to have sort of these 3 rows. Each sum in a column depended on what happened in the previous column in the same row. And so it kind of makes sense that there ought to be 3 base cases, the case for 8, 9, and 10 in our proof. All right, well, taking a look at these, please let me know if you have any questions on strong induction, and I'll see you later.